Hi, I'm Darren and welcome to Level Up EE Lab. This is the second episode in this series that I'm making on this IP-20 power supply repair. And today I'll be getting into the circuit design and start getting really technical. So stick with me because here we go. Remember that block diagram that I showed in the last episode? Well, we can toss that aside. It had issues, so I made some changes to the design, and here's revision B. The big issue was the lack of stability. There was just too much phase delay in the feedback loop, and I gave up on trying to make it stable. Now, I did get some great tips and some help from some members over on the forum on EEVBlog, and that's what's led me now to this new design. So let's look at the changes. The big one is switching from high side to low side current sensing, and that seemed to make all the difference in the world of fixing the stability problem. So that eliminates the current sense amplifier, and I'm now taking the voltage drop across a low side sense resistor as an input into the op amp along with the current limit set point voltage. As before, the op amp will pull down the voltage regulator whenever the current exceeds the particular limit. Smaller change, I also lowered the 8 volt supply to 5 volts because when I changed to low side current sensing, I also changed op amps to fix another issue. The op amp I had in there before just could not pull down low enough to the low rail. And the new op amp, well, it only works up to about 5.5 volts, so I had to get rid of the 8 volt supply, but no big deal there. So next up is to actually dive into the circuit designs that I came up with based on this diagram. So let's begin that with taking a look at the bridge rectifier and the filter caps board. Here's the schematic for it. Now, it is pretty simple. There's 4 diodes, but notice they're not 1N4000 series. Now, those just won't work. They're only rated for an amp maximum, and I need at least 1.5 amps. Lots of options, but in this case I chose 6A10s. They're overkill. They're 6 amp, 1000 volt diodes, but I have a lot of these in my stash, so I might as well use some up here. The original capacitor is 3000 microfarads, 75 volts. Now that's not enough capacitance for my design. I'm going with more than double that at 6600 microfarads. And rather than one big cap, I split it into 3 2200s put in parallel. The inrush current to charge 6600 microfarads is definitely a concern. There are several techniques to deal with that, and a common one is to use an NTC thermistor. That's not feasible here because the current is not steady state. It would just not get hot enough and stay hot. I could also go with a MOSFET here as a pass transistor, but that's kind of overkill, so I just went with some series resistance, just 0.5 ohm in this case. I can tolerate that additional voltage drop, as we'll see in a moment. Now, based on the ESR of the caps I've chosen, putting that resistance in series drops the peak inrush from over 400 amps total for all 3 to 25 amps for all 3. That's more reasonable. I'm still going to need a slow blow fuse on the AC line. The maximum voltage the circuit will see is about 60 volts. So 100 volt rating for these caps might seem excessive, but the next lower commonly available voltage rating is 63 volts, so that's definitely not enough headroom. And then lastly, the 6.8K bleeder resistor. That's the same value as the stock unit. And I'm pretty flexible of what I can use here. A lower value will discharge the caps faster, but of course will consume more power, so there's always going to be a trade-off there. A better way to look at it is this hazardous? 60 volts is considered hazardous by OSHA. Anything above 50 volts gets into that hazard territory. So let's look at it from a dissipation standpoint. How long would it take the 6600 microfarad charged caps at 60 volts with a 6.8K ohm resistor across them to discharge to 50 volts, and then how much longer to drain off, let's say 95% of the charge? Well, it's a simple calculations to show that it'll take about 10 seconds for that voltage to decay from 60 to 50 volts, and just over 2 minutes to drain off down to 95% of the charge. So I think I can live with that. I think that's a good compromise. Okay, so 6600 microfarads. How did I come up with that? I'll walk through the calculations here in a moment, but like I said in the first episode, there's a lot of interactions between the functional blocks, and some of those have a direct input into why I went with 6600 microfarads. Bottom line, it's all about the voltage drops ahead of the regulator. And to figure those out, it means taking a look at where those drops are coming from. So let's jump over to board number 2. Now, there's a lot going on here in this schematic. I'll get into the details in the future, but for now, these are the key takeaways. So let's start over here on the left. The output from board number 1 comes in here into switch CR-1. Now, the job of this switch is to select an appropriate sense resistor for the current meter, which will introduce some voltage drop. Now, after it, there's more voltage drop. There's sense resistor R15, and it's pretty substantial at 3 ohms. This is a shunt resistor that controls these 2 bypass transistors. Then finally, the DC flows into an LM317HV linear regulator. Yeah, the 317, it's an oldie but goodie, and I have several reasons why I'm using one for this project. The biggest one is the HV version can tolerate up to 60 volts input to output. No other regulator can do that. Not even the LT3080 family can do that without additional circuitry. Now, unfortunately, the 317 does have a high dropout voltage. These modern regulators are much better. They're in the order sometimes of just a few tenths of a volt, but the 317 is upwards of 2 volts worst case. Nevertheless, I can still tolerate that much dropout in this circuit. Now for the calculations of how I got to 6600 microfarads. So on this spreadsheet, I'm showing a lot of numbers, but let's start with looking at what are in these blue cells. These are my inputs to the calculations. And the first value that's input is the full load current of 1.65 amps. Now remember that the fine current limit adjustment on this power supply goes up to 110% of the course setting. So 1.65, that's 110% of 1.5 amps. Next input is a number of diodes. I have to account for the diode drops. There are 2 of them. I'm using a bridge rectifier, so there's always going to be 2 of them in the DC power flow. 5,280 microfarads. Well, where did that come from? I said I was using 6,600. I'm discounting it by 20%. If you look at the tolerance on most of these generic filter electrolytic caps, they're plus or minus 20%, so I'm factoring that in. Then these next 3 are the shunt and other resistors that are in series that are going to have voltage drops. The big one here is 3 ohms. That's that bypass, that's that shunt rather that drives the bypass transistors. Second one, I do have 0.5 ohm of inrush current limiting resistance that I talked about earlier. And this third one, 1/10 of an ohm, that's a small shunt that's in there to drive the analog meter. Now this varies depending upon how you have the course current limit set, but in all cases it's the same voltage drop for the same max current. So in this case it's 1/10 of an ohm. Now the first item I want to calculate here is the maximum current going through the 317. I have those bypass transistors there for a reason. That's to limit how much power that 317 has to dissipate. So let's jump back to the schematic briefly. And if we look at how it works here, transistor Q2 is normally off, but once the current gets to a certain point, it'll increase the voltage drop across R15 until it reaches about 700 millivolts, and that's enough to turn on the base emitter junction on Q2 and cause it to start conducting, which then feeds current to the bases of Q3 and Q4, turning them on and letting them absorb, if you will, or bypass any current above whatever they got triggered on at. So I can calculate that maximum 317 current using Ohm's law. So 700 millivolts divided by 3 ohms is about 1/4 of an amp, 233 milliamps to be more specific. So that's what I'm limiting my 317 to. And I have to split that out separate from the full load current, because if you look at that schematic, the full load current doesn't go through everything that's on that schematic. And again, it's all about voltage drop. That's what I'm trying to get to here. So now that I have these figures, the other inputs in these cells here all come from either the Heathkit manual, in this case, the course voltage setting in DC, or the nominal AC RMS value coming out of the secondaries. Now, these 2 columns come from the first episode where I measured the actual voltage, unloaded and loaded at 1.6 amps. This is important because I wanted to know just how much headroom I have here for this power supply. And my values, of course, are slightly higher for unloaded, mostly because I think it's 125 volts mains that I'm working off versus 117 volts that was in the specs. So, It's only a few percent high, but nonetheless, this is the most important column. This is the loaded AC RMS that I have to work with. So with these inputs, I can now calculate the DC max and DC min. This is the ripple coming out of the first board going into the voltage regulator. And I'll pause here so you can see the formula up here at top for how I calculate the max. And then here's how I calculate the min if you want to study that a little more closely. And this guy over here, this is the actual formula that makes up that minimum voltage. The ultimate goal here is I want to make sure that the difference between what's in this column here is the bottom of that ripple, the valley of the ripple coming in, is significant or satisfactory, I should say, higher than the maximum voltage I'm trying to get out of the regulator. And this column L calculates that difference. So that needs to be at least 2 volts minimum. And as you can see with these values here, it's not a problem. In fact, there's an excessive amount of voltage when you get up to the 50 volt output. And in particular, 21.7 volts is way excessive for margin on the regulator. And the side effect of the course is it's generating all kinds of extra heat, wasted power being dissipated in the power supply. So naturally, one of the big changes I can make here is reassign these secondary taps. In other words, I don't need to feed this tap in this design to get 50 volts out. I can go back down the ladder, if you will. And in fact, I can go back down 2 taps here. I can pick 45.1. That's the 1.6 amp loaded tap at 40 volts. If I put that in for 50 volts, I still have satisfactory margin at my regulator. And look what I've done. I've cut in half pretty much the amount of power that the power supply is going to be dissipating. 25 watts is still pretty substantial, but again, this is a linear power supply. It ain't going to be efficient. The big takeaway is I'm going to greatly reduce the load that are on those transistors. I'm going to be 11 watts maximum versus 20, just over 20 watts maximum. So that's a big improvement right there. So finally, I can get to the big question of why did I pick 6600 microfarads? Well, it was an iterative process, and one of the quick iterations to show here is, well, what if I drop it from 3 of those caps to 2 of those caps? Easy enough to do. Then the calculations update, and I see a problem right there, and I see a problem right there. That's not enough margin at the regulators. That's not enough capacitance. My minimum DC voltage, my ripple had increased, so my minimum voltage fell even further. So now I'm risking having my regulator start to drop out. So I can't go that low. I need to be at least 3 2200s to give myself sufficient headroom at my regulator. I mentioned earlier that I gotten some great help from some folks over on the EEVBlog forums. So what I've done is included a link to that discussion thread in the video description below. Do go check that out to see more details about how I got from the last episode to where I am in this episode. Now, looking ahead to the 3rd episode in this series, I'll be getting into great detail on that main circuit board, which includes the LM317, the bypass transistors, the op amp that controls the constant current mode, and a bunch of simulation results that have given me enough confidence that I've got a stable enough design here to move forward with doing board layout, which will probably be in the 4th episode. This has turned out to be not a trivial project. I've learned a lot about how challenging building a linear power supply can be, especially when you're trying to make one that operates stably and doesn't have a bunch of unpredictable behavior. So I do hope you've enjoyed the series to this point, and I do hope you'll stick with me as I progress this project over the next several episodes. So until next time, bye for now.